All right. Well, hopefully all of you are well hydrated and well fueled for this adventure on Kafka and Flink. Welcome to ANT342, where we'll talk about operating Kafka and Flink at scale using our managed services. My name is Sai Mitali. I lead the product teams for our managed Kafka and Flink services here at AWS. As a dad of twins, I thought I had enough at home. And then I ran into the two twins at work, Kafka and Flink. So my twins have a very interesting story. They look exactly the same. They're born the same day of the week, the same day of the year. Obviously, they're twins. But the twist is they're born years apart, about 6 years apart. I think the story is very similar with Kafka and Flink. Born years apart, Kafka and Flink have now become inseparable twins of streaming data. My friend Ali here has a similar story. Ali?
Hi everyone, Ali Alemi here. I'm a senior streaming architect at AWS. I'm a father of twins too, and my twins are exactly the same age. As father of twins, I thought I have my hands full already until I met Apache Kafka and Apache Flink. So like my twins, they play nice with each other, but like them, twice the fun, twice the challenge. But don't worry. Like with our twins, there are strategies to manage Apache Flink and Apache Kafka at this scale, and that's exactly what we are here and talking about.
Well, speaking of which, let's quickly cover what we want to do in this session today. First, we'll start with what is data streaming and why are customers interested in data streaming. And then we will talk about why people are turning towards Kafka and Flink to build these streaming applications. And then we will do the adventure on Kafka, what it takes to run Kafka at scale when you're managing it on your own versus how easy it is with our managed services. We'll do the same thing with Flink. Ali is going to come over and talk about Flink. And finally, we will leave some time for questions. Does it sound like a plan? All right, let's start with why streaming. What customers routinely tell us is there's never been a better time to build streaming applications. Here is why. These customers have realized the value of real-time insights. A lot of us are banking customers, right? Do you want your fraud alerts now when the event happens, or do you want them an hour later or days later? Of course, we want them in the moment. If you're a retailer, do you want to have access to your real-time inventory? Absolutely yes, because I want to make sure products reach customers on time, and I can actually optimize my costs. I'm sure a lot of you are SREs or have done SRE work before, like a site reliability engineer. Do you want access to alerts when the event happens or an hour later? Of course, when the event happens. As you can see here, real-time insights are extremely valuable for timely business decisions. Cost continues to be in the top of the mind for all of us. With streaming data, it gives you the opportunity to filter noise and get to the signal very quickly. As an example, let's say I am managing a website. I'm interested in capturing specific user interactions, just like purchases, for specific users. So one approach is to collect all the data with all the users and all their interactions, store it, and then process that every time I need some of the insights. Comparatively with streaming, I can capture all this data as it's getting generated, filter for those interactions that I'm most interested in, and thereby, I'm saving on compute and storage costs. The third big reason why customers are turning to streaming data is to keep their systems in sync all the time. Imagine if I'm a food delivery company. I need to scale to millions of transactions at any given point of time. And hence, I embark on building microservices applications where each application is purpose-built to do a specific activity. But the core important thing is to make sure these systems are always in sync, and streaming data plays a vital role in moving data across the enterprise. So when a customer calls about an order, the sales rep picks up, or the customer service representative picks it up, they have access to that information in real time. That improves the overall customer experience. In summary, streaming data can help customers achieve great results and help deliver better outcomes to the end users. To build streaming applications, like I said before, customers are turning towards two very powerful technologies. Apache Kafka to capture large volumes of data at really low latency, and then use Apache Flink to process the data to generate real-time insights. Interestingly, like my twins, Apache and Kafka, born years apart, but share some really common characteristics. Let us see what those are. First is they support a diverse set of use cases. I could use Kafka and Flink to capture data, transform it, load into a lakehouse, use it to load data into an iceberg table, and then process for in-depth analysis. I can also use Kafka and Flink to build my microservices application or event-driven architectures. I can use Kafka and Flink for real-time analytics like fraud detection, anomaly detection. So it can both serve a diverse set of use cases. They also come with specific features around fault tolerance and processing guarantees like exactly ones that allows developers to bring these use cases to life very quickly and very easily. They also support a broad range of integrations. What that helps you to do is to integrate Kafka and Flink with a broad variety of systems in your enterprise. AWS provides a lot of out-of-box integrations with managed services, some of which we have contributed back to the open source community. Both also have scale-out architectures. What do I mean by that? Which means that when you have more data to process, both can scale, and so that way you're not worried about scaling cliffs. Lastly, both these technologies are backed by strong community, which means that you get access to constant innovation that is built by several companies into the open source ecosystem. And you can upgrade and get the latest and greatest features each time. So as you can see here, streaming data has immense potential for customers. And Kafka and Flink are the go-to technologies for people to build applications. Then a foundational question comes to my mind. What does it take for customers to build 10x more use cases on streaming data? When we ask customers, they do tell about certain challenges that come with Kafka and Flink. How many of you have actually used Kafka and Flink or operate Kafka and Flink today? Well, if you are, hopefully some of the things on the slide are resonating. They're not easy to set up. They can be tricky to scale. And it's not easy to achieve high availability out of the box. And in this session, we will see why. Maybe we'll agree, maybe we won't, but we'll just go through that process. The last key thing on this slide is it can get expensive to maintain at scale because you have to keep up both operationally and also from an infrastructure cost standpoint. And what customers are doing, though, is because these challenges remain, they're turning towards AWS managed services for Kafka and AWS managed service for Apache Flink. The goal of these two services is to address these challenges whereby you're offloading the infrastructure management, the undifferentiated heavy lifting to the AWS teams, and you can focus on building Kafka and Flink applications or run Kafka and Flink clusters. And we'll cover through this presentation why that is the case. Customers across a broad variety of industries in all sizes are using managed services for Kafka and Flink. Somebody like Orchard uses Amazon's MSK to reduce the time to synchronize databases from hours to minutes. A customer like Nextthink is using MSK to stream trillions of events and being able to scale for this massive throughput with a small member team. And then my favorite use case, which is NHL. How many of you are hockey fans? NHL uses Flink, our Flink managed service, to essentially calculate and predict face-offs when two players are together or are facing off, and a puck drops. It essentially is calculating the probability of who wins. It's a good example of how NHL is using Flink and other services to change the viewing experience. So it comes to my 7-year-old popular question, which is every time I tell her, you can do this, the next immediate question, can anybody guess? Why? Why? Right, so let's talk about why are these customers turning to managed services. To do that, let's start with Kafka, and we will go through what does it take to run Kafka at scale. And what I wanted to do was go through the paces of an administrator would go through to manage Kafka. So typically, you're spending time in any of these three activities. Either you're planning, provisioning clusters, or you're operating them with high availability. You all get paged, right, when things don't go well. Or you're scaling the infrastructure. You're making changes to the cluster. So what we will do is we'll go methodically through each of these spaces to see what are the challenges and how managed services help. Let's start with, well, before we actually go into these activities, I want to start by covering two foundational concepts with Kafka. The first thing I want to start with, a typical Kafka cluster has a bunch of brokers, right? And each broker has two aspects. One is a compute layer, the other is a storage layer. The compute layer is responsible for serving requests, authentication, authorization, making sure semantics are maintained, item potency of the producer, and things like that. The storage is responsible for laying out the data, making sure things are stored in a durable fashion. It's able to reason with configurations that you are setting so that data is durably stored on disk. Because Apache Kafka was born on-premises, compute and storage were deeply coupled together. In most cases, the storage was living on the compute node. What it means is the failure modes for both are tied together. So when you lose a compute node, you're essentially rebuilding all the storage as well because the storage is on the compute node. When you move to the AWS cloud, some of these failure domains become a lot easier because typically in the cloud, you're using a network attached storage like EBS. So compute and storage failure modes are fairly separated. So you could lose a broker, an EC2 instance, comes back online, the storage is still around. So the mean time to recover from a failure is much better compared to what you see on on-premises. You also benefit from AZ resiliency that comes in AWS cloud, which means that you're more protected against infrastructure failures like power failures. However, certain things remain the same because you're taking the same Kafka software running on AWS cloud. As an example, you got to think about scaling compute and storage together. So if you need more compute, you add nodes. That also means it brings more storage. You want to retain more data, you want more storage, you add a node, that also has more compute. So this separation drives some interesting behavior on how to think about provisioning and scaling. There is another, so we talked about compute storage coupling. There is also another coupling that is actually not talked as much. And I want to demystify that today. So to understand that, let's start with a typical setup. You have a Kafka cluster. In this case, you have 3 brokers. And brokers have partitions. In Kafka, partition is a unit of storage. In a typically well-configured cluster, you have a leader partition, and it has a couple of replicas. For high availability reasons, replicas run on different brokers and typically in different AZs. Writes go to the leader partition, and then you should also consider data that needs to be replicated. So as a write goes to a leader partition, that is replicated to the replicas on 2 different brokers. Now, you could also have leader partitions on other brokers. So in this example, the producer is writing to partition 1 on broker 1. It's also writing to partition 2 on broker 2. And in both cases, data has been replicated back to replicas. So when you're provisioning a cluster and you're provisioning compute and storage, you have to consider not just write and read throughput. You should also think about replication that goes into the broker, out of the broker. You should also plan for failures. Failures can happen, and you want to make sure you're planning for those. Let's read through what happens when you lose a broker. In this case, broker 2 is unhealthy. You detect that it's unhealthy in a self-managed environment. You stop Kafka. And when you do that, what typically happens is Kafka detects that a leader is unhealthy or the broker is unhealthy, and it basically fails over the election, or rather elects the replica, in this case partition 2's replica, on broker 1 as a new leader. Because you have a new leader now, all the writes from this producing application are going to partition 2 on broker 1. And consumption also goes to this broker. What that actually means is broker 1 now has to ingest 2x more data. So you need to plan a buffer to handle failures for all the brokers at any given point of time, because failures can happen at any given point of time. Let's play this along. After a while, broker 2 is healthy. So you bring that broker back up again. And then what Kafka does, it has to catch up the broker 2 because it was down for some time. Let's just assume 30 minutes. Now it needs to catch up for data that was produced in the last 30 minutes. The interesting thing about Kafka is it doesn't have really the sense of separation between application traffic and the system traffic, which is in this case rebalancing, recovery, or things like replication. So what that does is, because there are no separations, if you don't configure the cluster properly, when it's going through a catch-up process, it starts impacting primary produce and consume on that cluster. So what? Well, if you're optimizing for faster recovery of the broker, it may end up impacting the overall availability of the cluster. So what do? You essentially plan a buffer for a catch-up scenario. Is that all? Well, there's one other failure mode that you want to think about, which is what happens when you have a slow consumer. This happens all the time. You could have a consuming application like a Spark job or a Flink job. That could have an application error, bad logic, or somebody did a bad deployment, and now it has fallen behind, which means that it was down for an hour. It now has to catch up for all the data that was produced in the last 1 hour. So you want to make sure you have a buffer to catch up when a consumer is unavailable. So what you can see here is provisioning is a multidimensional challenge. You not only have to think about the ingest and egress traffic, that is what your workloads need, but you should also think about the background traffic or the system traffic. In this case, it's a replication traffic. It's a catch-up that you need to recover from failures. It's also buffer you need to recover from slow-consuming applications. Once you have these, you have to go think through what is the instance and volume specification. Am I selecting an X large instance? Am I selecting a 2X large instance? And now you take all these inputs, you take all those specifications, and you can arrive at a cluster specification. Sounds complex, isn't it? We got you covered. So let's go through this step by step, right? So the first step is to look at your instances, EC2 instances, and look at the quotas. Benchmark CPU and RAM requirements. Now, Kafka largely is a throughput-based system, but there are cases where it is CPU-bound. There are cases where it's memory-bound, and you want to consider those. Then you go look at your peak throughput, not average throughput, but peak throughput, because you want to make sure you have enough capacity for that peak traffic that you may see in a day or in a week. And then you calculate the amount of memory and CPU you need, and then you go to storage. You think about how much EBS throughput you need. You think about how much EBS storage you need, how much network throughput you need. You take all these values, and then you divide that by the instance quotas. You arrive at a cluster configuration. All right, so now we have done the first part of the journey. We've got a cluster up and running. And the next part of this journey is to run this with high availability. The first place to start with is to make sure you have the right Kafka configurations. Let's talk about 3 of those. The first is a replication factor. Like I said before, a Kafka is a leader-follower-based system. So a replication factor dictates how many followers you have for a leader partition. The best practice is to always have RF3. It's in 3 different availability zones. As you saw in a prior example, that gives you the best shot having a highly available, highly durable system. Then there are also durability configurations that you have to be very mindful of. First is minimum in-sync replicas. This dictates how many minimum replicas you want and in sync, and this gives you better tolerance against your data durability issues. The last and the most overlooked configuration is unclean data election, which you have to set it to false. And the simplest reason being is it allows and makes sure that a follower that is behind doesn't become a leader in case of a failure. So these are 3 simple configurations, but they are not it, right? Kafka has 8 different categories of configurations across networking, performance, storage configurations, right? And in not all cases, defaults are great. A good example of this is number of I/O threads. Now, when you have a large instance, you want to push more throughput to it, make sure you have the higher number of I/O threads. And at the very same time, also make sure you have the network I/O threads are also higher. Otherwise, you will see queue saturation in certain scenarios. You should also be careful about using a very high value. And I want to illustrate that with an example. There was one large customer who had a 60 broker cluster, and they had a very, very high configuration value for a setting called number of replica threads. Number of replica threads essentially allows you to catch up and recover from a failure very quickly. But we talked about this, right? There is no good separation of foreground I/O and background I/O in Kafka. So if you have a very high configuration, what ends up happening is you're obviously catching up very quickly because all the prioritization is now about catch up, which means that you don't have enough resources for produce and consume. So because of that high configuration, what ended up happening was the customer was prioritizing broker availability over cluster availability. And they were seeing high write latencies and read latencies while the catch-up was happening, which lasted several hours. So one of the best ways to deal with this is to test and validate your configurations, and also protect your configurations from accidental mistakes that developers make. I'm sure all of us have dealt with RF equal to 1 topics, right? And they can happen because a lot of times those are topics created by developers who may not fully understand the implications. The second key thing about running an efficient and highly available system is to have the right metrics. And I want to give a couple of examples for this. Let's see. how many of you ever got paged by disk full on Kafka? Well, quite a few of them. Well, Kafka doesn't like a disk being full. When a disk is full on Kafka, what typically happens is the broker essentially goes into a tailspin. It goes through an unclean shutdown, and then you are spending time to manually recover the broker. Also, adding storage is not something that can happen very quickly. You can't keep adding more and more storage in real time in some cases. So you have to plan ahead. You want to make sure you have the right monitoring in place to make sure you know what your utilization is, make sure you have enough headroom for growth that you may see in the next day or two. And whenever you're hitting at a 60% utilization or 80% utilization, you want to add storage proactively. Because like I said, the mean time to recover from a failure in Kafka is very slow for some of these use cases. The other typical pattern where we see customers running into issues is when they run out of volume throughput. Now, the challenge with this is it doesn't show up directly. So the typical failure path is you run out of volume throughput, you see a lot of requests getting enqueued, and then what you see is a high CPU I/O wait time. Acknowledgements for the leader partitions for other brokers are taking more time because this broker is unhealthy. So what will happen immediately is you'll start seeing cluster being unstable, and recovery of that is also going to take more time because you've maxed out throughput. The only way to get out of that situation is to essentially reduce the amount of traffic that you're driving to that cluster. Again, a good example where not being proactive and monitoring and alerting can drive a cluster-wide instability. So these are two good examples where you need active storage management to run a highly available Kafka system. The third big aspect where customers spend most of their time is scaling. Change is inevitable, right? You provision a cluster, you're operating that with high availability, but lo and behold, changes come. You're either onboarding a new workload, a new team wants to stream data through Kafka, you have more throughput to handle because you candidly have more business, that is great generally. Or you want to improve your security posture, or you want to reduce the number of brokers you have because you want to optimize your costs, but change is inevitable. And what change also means in Kafka is a rolling restart. I don't know if there are too many fans of rolling restarts in Kafka. It's because it is a complex process. But let's try to simplify that through this whiteboard. So I'm going to take the example of vertically scaling a cluster. So you're going from 2XL instance to 4XL instance. So let's see what you go through. First is launch a new instance. You make sure to install Kafka. Make sure it's the same version. You set the right configurations. It should always be in sync. You install certificates, the right certificates from a security standpoint. Start the Kafka process, monitor that it's joining the cluster, make sure it's fully caught up. The one of the things that you don't see on the slide, which is super important, is the order in which you're doing rolling restarts. You should always make sure the controller node is the last one that you're restarting. Otherwise, what ends up happening is you have the controller moving all over the place, and the cluster will start seeing instability issues, stability issues, and you will start seeing consumer timeouts, higher write latency, and things around that nature. So again, these are best practices that you want to follow every time you're making changes to a Kafka cluster. So another way to add capacity in Kafka is to add more brokers. So in Kafka, what happens is you add brokers, and then you do this thing called partition rebalancing. And where rebalancing partitions, you are actually moving data from one set of brokers to other set of brokers. And that, as the slide shows, it can take hours. Now, what that means, because it's a time-taking activity, it also can be impactful for your applications if not done well. And there are some learnings that we want to share today. Always make sure you have enough bandwidth available for rebalancing. Because, like we discussed, there isn't really good resource separation in Kafka. Everything is super coupled. So make sure you have buffers for rebalancing. Because interestingly, rebalancing, if you don't have enough buffer, you're deciding whether I rebalance fast and actually complete the scaling activity, or do I impact my application traffic? You don't want to be in that zone. The second thing is you have to be very careful about how you're orchestrating rebalancing. You don't want to move more than 20 partitions at a time, because like I said, you're moving a lot of state, which has a claim on the resources on that broker. You don't want to run it super hot. The third important thing is you want to constantly monitor that activity, because you may start at some point, things change in the cluster, and you may want to choose a different plan. And there are tools out there like Cruise Control that allow you to plan and do this rebalancing in a way that doesn't impact your applications. A last bonus point on this one. It's also super important for you to start this very early. All right, so of course, we want to make this easier for customers. And 6 years back, we've launched MSK to make it super easy for customers to run Kafka applications. And since then, our biggest mission has been, how do we make it even better for customers to run Kafka on AWS? As we have run storage systems like EBS and S3, we've had the opportunity to learn about elasticity and resiliency from those systems and bring those to Kafka on AWS. More specifically, we asked ourselves, storage management seems to be very complicated. How do we simplify that for customers? How do we simplify resource coupling in Kafka? How do we make compute elasticity easier for customers so that they can scale up and scale down capacity in minutes? How do we get all these best practices codified right into the product? The manifestation of all of these is us reimagining Kafka on AWS for high performance, high elasticity, called Express Brokers for Amazon MSK. We launched this new broker type in general availability 3 weeks back, and it's available for use for customers. Let's dive into that. The first big piece of Express Brokers is it eliminates storage management. Remember the disk full issues that we talked about? Those are not an issue with Express Brokers. So you no longer worry about provisioning or sizing storage capacity on Express Brokers. That is something that is responsible by, that is something that AWS handles. You also get unlimited storage capacity per broker, which means that disk full is no longer an issue. The second key element about Express Brokers is you're also not worried about doing configuration management with storage. What segment sizes you pick, number of replica fetchers, all of those are controlled by and managed by AWS. The last thing is my favorite part of this, which is you pay for the amount of data you're retaining. You choose a retention period, and you're paying for what you're retaining, not for provision capacity, not for 3 different copies in 3 different availability zones. That essentially allows customers to save up to 80% cost in terms of storage with Express Brokers compared to standard Apache Kafka. The other thing is we have simplified provisioning significantly with Express Brokers. So remember the calculation that we went through? That is not a thing with Express Brokers. Each instance size tells you how much of write throughput and read throughput that you can do. So if you want a 45 megabytes per second cluster, you provision 3 brokers that are large, and you're done. If you want more, you select 4x large brokers. So sizing is dramatically simple with Express Brokers. And then Express Brokers also deliver more throughput per broker, up to 3x. So let's look at a sustained throughput as a way to think about what it is for standard Apache Kafka brokers. In this example, we have M7G brokers. And as you can see here, it's sustained throughput. What I mean by that, this is the amount of throughput that is available for your applications after factoring all those buffers that we talked about. Comparatively with Express Brokers, each broker type does more throughput than standard brokers. As an example, with 2x large is about 25%, with 4XL it's about 33%, and all the way up to 16x large it becomes like 3x or more. This, our customers say, is game-changing because now you can run a significantly large cluster with fewer brokers. As an example, with standard brokers, you need like 20 brokers to run a 3 gigabytes per second cluster. Comparatively, with Express Brokers, you can just use 6 brokers. This allows you to get more per each instance and run more agile your infrastructure. The next big piece is, of course, you've done the provisioning, you've got it up and running, all the best practices are codified. Now it's time to scale. And you have 2 options to scale with Express Brokers. The first is vertical scaling, the next is horizontal scaling, and let's dive into each one of them. With vertical scaling, it's a single click changing the instance type from, in this case, let's say, X to 4XL. You go to the console, make the change, and MSK takes care of the underlying orchestration. And we do that in a way that it doesn't have any impact on applications or any durability impact. We also have guardrails in place to make sure there's a safe rollback if things go wrong. Express also delivers game-changing elasticity, 20x better than standard brokers. We talked about this, right? In Apache Kafka, a typical rebalancing activity can take hours. The way I talk about it is like driving on a freeway on a Monday morning. You need a lot of planning, and disruption can be eventful. Comparatively, in Express Brokers, rebalancing takes minutes. So for a well-sized cluster that's doing a 300 megabytes per second, with 6 brokers, moving 3,000 partitions takes under 5 minutes with express brokers compared to hours with standard brokers. What that actually means is now you can scale up and add brokers and remove brokers in minutes. So if you have this peak event that you're preparing for, you're very confident that you can add brokers without any impact to your applications. So all that planning and orchestration that you have to do is no longer necessary with express brokers. The next big piece about express brokers, it's designed to run mission-critical applications. And there are 3 big reasons. First is all the best practices are codified into the product. So you're no longer worried about a developer configuring a topic with RF equal to 1 or min ISR settings. Those are built into the product. Second is, we talked about this, right? Express brokers come with resource separation. So that way, application and system traffic don't compete with each other. So you know for a fact that you can drive X amount of throughput per broker, and you always get that guaranteed throughput. Failures do happen with infrastructure. And when failures happen, express brokers recover 90% faster compared to standard brokers. So if you lose a volume in express brokers, the recovery takes about 5 minutes compared to standard Apache Kafka, which can take hours. What this does is it actually simplifies your mean time to recovery, and thereby you can run most critical applications without a lot of overhead. What we've also made sure with express brokers is that there are no hard compromises. What do I mean by that? It's 100% Kafka, which means all Kafka applications work with express brokers. The second big thing is it has the same low latency as standard Apache Kafka. You have chosen Apache Kafka for its low latency, and we didn't want customers to make that trade-off. The third thing is it has all the MSK features. MSK Connect, support for schema registry, MSK Replicator that allows you to, and also things like MTLS, SASL Scram, that allows you to migrate your applications without any changes to your infrastructure. And the last thing is it is designed to operate at a very high scale and deliver the best price performance at any scale. So now with express brokers, you have 3 choices with Amazon MSK. You've got standard brokers, you've got express brokers, and MSK serverless. Now, people ask me, when do I choose what, right? And the best way to do that is to compare that with standard brokers are like your manual your manual car, right? For people who want the control, who want that flexibility, who have got deep expertise in Kafka, they give the best price performance. And of course, you're still having AWS manage Kafka infrastructure for you, and you're managing Kafka operations. On the very right-hand side, you have serverless, and serverless is designed for one-click Kafka. I create a Kafka cluster, I'm done. But if you need something in the middle which has the elasticity and scale up and scale down, you want the automation, at the same time, you want the best price performance and the ability to operate Kafka at any scale, that's when you choose express brokers. Now, unless you know differently, our recommendation is to start with express brokers for all Kafka workloads. Given its price performance, given its elasticity benefits, given its resiliency benefits, we think it's the best place for people to run Kafka workloads at AWS. What if you want more resiliency beyond a single cluster? For those type of use cases for disaster recovery, we've got MSK Replicator. MSK Replicator is a single-click way for you to add additional resiliency to your Kafka clusters. It requires no planning. You don't have to manage any bespoke applications. You go to a cluster, enable Replicator, and we take care of replicating data across clusters. The next feature that I do want to talk about before I hand over to Ali is about multi-VPC connectivity. This is a feature that is useful when you have different applications running in different AWS accounts, and you want to make it simple to connect to a central AWS cluster, an MSK cluster. This feature makes it a single-click experience for you. So just to wrap up, with MSK, our goal is to make it easy, cost-effective, and extremely reliable for you to run the most critical Kafka applications on AWS. With that, let me hand over to Ali.
Awesome. Thank you very much. So Sai raised a lot of interesting points about Apache Kafka. Let's talk about the other twin, shall we? All right, let's just start with planning. Let's get started with the developer experience with Apache Flink. Apache Flink provides multiple APIs for developers to be able to build an Apache Flink program. At the very top is Flink SQL. So Flink SQL is the easiest way to get started with building Apache Flink application. what we are seeing is it's data analysts without any programming knowledge, they can get started with Apache Flink very quickly. They can experiment with the data. They can interact with the streaming data like they're interacting with the data in a traditional database. We also see developers need a little bit more flexibility. And then that's when the other APIs become relevant. Table API is a little bit more flexible because it gives you access to the primitive of programming languages such as Python, Scala, or Java. You can do more, and you still get the same abstraction and the expressiveness of the SQL at the same time. What we are seeing customers mostly use for complex applications in production in continuous mode is data stream API, because they get the most flexibility in terms of controlling the real-timeness, the windowing, the complex aggregation using the APIs that the data stream API provides. There are also use cases that developers want to write their own operator. And they use process function API for that. That's the most complex. That's where in Apache Flink development it gets more complex. But then at the same time, you get the highest flexibility by getting access to state and timer of Apache Flink. I show this slide because it's important. If you're planning to build a platform to manage Apache Flink workloads at highest scale, it's important to build a platform that supports all these APIs. Otherwise, we will limit our developers to only one single API, which is not going to fit best for all size of workloads and all complexities across the workloads. All right. Next thing we need to understand is Apache Flink anatomy. In Apache Flink, there are two types of processes. There are processes that they run the computation over the events in the data stream. Those are known as task managers. And there are other type of processes that they are in charge and responsible for orchestrating the task managers. They're known as job manager. So Flink provides multiple deployment modes. And the application mode is the most recommended way for building and deploying an Apache Flink job, because you get a dedication in terms of isolation and dedication between different jobs, and you get a dedicated job manager, you get a dedicated cluster per each job, and that isolates that job to any failure that could happen as a result of hardware or other things that could fail, only isolated to that single job. That's the recommended deployment mode, and I will talk more about the deployment job, how is that relevant to our planning. And then in a deployment mode, when we deploy Apache Flink cluster, we basically will get one single job manager and multiple, usually more than one task managers. What job manager does after the deployment is scheduling the tasks into the slots that provided by task managers. We'll talk more about the task slot and the task itself and the relevance of it to the parallelism. But at this point, we need to understand the task managers need storage. Why do we need storage here? Because Apache Flink is a distributed and a stateful system. So it needs a storage to store the data, to memorize the result from the previous operation and roll it into the new events as it processes and moves forward. But what happens when something goes wrong? What happens if the task manager process crashes? What happens if a task manager is failing because of a hardware failure? So then we need another backup storage. We need a cost-effective, highly durable, highly available storage in order to basically send a backup. So when we lose the node, when we lose the hardware, when the process crashes, we don't lose all the data. Apache Flink provides a mechanism called periodic checkpointing. Periodic checkpointing sends a snapshot of the local storage to a durable storage and keep it there. In case the job fails and the task manager restarts, it can then retrieve that previous snapshot and resume from the previous checkpoint. Apache Flink also provides the API for the operators to take a backup of this state. So basically, the same periodic checkpointing, which is automatic in Apache Flink, could be done by operators and take a manual backup, and then you can then take that backup on the durable storage. So what all of this means in terms of our planning, what do we need to do? What do we need to provide? All right, so first, we need a capacity provider for our Apache Flink cluster. We have two options. These are the most popular one, Kubernetes and Yarn. So these are the resource providers that provide the compute, local storage, and memory for deploying an Apache Flink cluster on which we will deploy an Apache Flink job. As I mentioned, there are other ways that you can deploy Apache Flink jobs. You can have single Apache Flink cluster, AKA session mode, and then you can run multiple jobs on top of that. You get single job manager for all the jobs, and then you get no isolation between the jobs in terms of resource utilization. Not a good idea for production, maybe a good idea in development and test, if you want to save on the cost of the resources. So you deploy a Flink job on a cluster in application mode, and then you need to provide also a highly durable and available storage, such as Amazon S3. Then you need to enable periodic checkpointing and set the configuration for periodic checkpointing, for example, the interval, how frequently the checkpointing should occur. And that also relates to how fast you want to recover, how much data you're willing to reprocess when failures happen. And then also you need to take manual periodic save points, because should you decide to deploy a new job and then have the new job resume from the previous job, you would need to provide it with the save point, with the backup. All right, so with all of that set up, now we need to set some retention policy in our low-cost storage. Amazon S3 is a very cost-effective storage, but when you have thousands of jobs, and each of the jobs take frequent checkpointing every 30 seconds, every 60 seconds, and then you also on top of that take backups, you need to set proper retention policies to save on the cost. And then you need monitoring. And monitoring is really important for scaling, which is something I'm going to talk about next. And then using the input from the monitoring, you would be able to build some auto-scaling capability. So when you detect that the job is experiencing longer latency than expected, or the job basically is consuming more CPU than is expected, then that's the time that you need to increase and scale up your jobs. We'll talk about the scaling next. All right. So how many of you who are operating Apache Flink clusters finding scaling Apache Flink jobs challenging? Quite a few. All right. This is because of the complexity that I'm showing in this slide. I'm trying to make it simplified a little bit by explaining why parallelism matters, what is the parallelism. So when developers build a Flink application, it's in the form of a couple tasks that they're chained together. Each task is going to be divided into task instances that they're going to run in parallel. The number of task instances run in parallel is called parallelism. If I have 4 task instances that they run in the same time, that is going to be my parallelism number, which is in this case 4. And then each task instance is going to process a subset of events. Because in data streaming, we have the concepts that we have the partitions and we have the shards, and then the data basically is going to store it separately. So then each of these tasks is going to process a group of these messages, not all of them. So what is the logical decision when I want to process more? Any idea? I'll increase the parallelism, right? So instead of 4 tasks, task instances, if I have 8 task instances, I'm going to be processing things faster. So if I have more throughput, I need to increase the parallelism. But is that really that simple? No, and I will talk about that, why. So before we understand how we can increase the level of parallelism, we need to understand the implication of it on our Flink cluster. How should we reconfigure a Flink cluster in order to match the parallelism that we need? As I mentioned, each task manager is responsible for processing the task, and each task manager provides a certain task slots as per the configuration you put in place for each job. The number of task slots you have available, that would basically provide the capacity the compute, the memory, the disk, and everything that you need for processing your task instances. And then you have, on one hand, hardware instances. You have compute nodes, for example, in Amazon EC2, wide variety of the compute types and compute sizes. And then on the other hand, you have parallelism. You really need benchmarking data, and this needs to come out from your testing to figure out how many task slots should be on each instance type and instance size in your cluster in order to scale up and match the parallelism that you need. So just quick recap. We need to monitor the job and then detect that we need to do a scaling operation. Then we need to find the new level of parallelism, which is, for example, double or whatever number that is desired. And then we need to, using the configuration that I mentioned, you need to figure out how many nodes, what type of nodes, and then you need to create a brand new cluster. And then you need to take a save point of the previous job and stop the job, and then deploy a new job on the new cluster and restart the job with the save point from the previous job. So that's the scaling operation we are looking at as per the best practices. All right, so let's talk about operating with high availability. How's that going to look like from the high availability perspective? So we talked a little bit about the task managers. They run things in parallel, and if any of them fail, we can restart them and start from the previous checkpoint. So we get some high availability with redundancy, right? Through the redundancy, we get high availability from task managers. What about the job manager? Yeah, we get some isolation when the job manager fails. Only one of the job fails because we are deploying in the application mode. But still, we don't want that to happen. The job manager is a single process, is basically becoming a single point of failure. How we can build a high availability around that? So Flink provides a high availability mechanism in this case. And first, we need to have more than one job manager, but they cannot be active. Only one job manager can be active, or known as leader, at any given point in time. And then when it crashes, we want another job manager to take over. But then who is going to determine that? Who is going to vote for which one of the job managers in the pool is next? So we need a voting system in place. And Flink provides a service for doing that voting on your behalf, but you need to provide it with either Zookeeper cluster or Kubernetes cluster in order to run a HA service, Flink HA service, to provide you that. And then through this process, the next job manager becomes the leader, and then the other job manager recovers and then goes back to the pool. So customers, similar to Apache Kafka, asked AWS why AWS does not build a service to simplify all this operation for us. We really want to just focus on the differentiating work. We want to build more streaming applications. We want to focus only on more modernization than doing undifferentiating work, building automation and all this benchmarking and testing that we need for planning and scaling Apache Flink jobs in our organization. So that's why AWS built a service previously known as Amazon Kinesis Data Analytics, which was the service to provide the Flink application and run it in AWS with a serverless infrastructure. And that service last year was rebranded as Managed Service for Apache Flink. So with Managed Service for Apache Flink, you can really get started with deploying a Flink job very quickly, and it's fully managed and serverless, and you pay as you go. And that's the best part of it. So you only pay for the number of the minutes that your job is running, and then once you shut down the job, if it's in the dev environment, if it's in the test environment, you can shut down the job, and then with some incremental, you will stop paying. And then also you will basically be relieved from all the undifferentiating working from the scaling, from planning, from provisioning, and security patches, and OS patches, and upgrades, and all that. So here's how the planning looks like with Managed Service for Apache Flink. A developer uses the idea of choice to build a Flink application in a local mode and test the application using the local execution environment, and then package the application in a form of jar or zip file in case of Python, and put it in an Amazon S3 bucket in one AWS account. Then the SRE team member or the developer goes and initiates the API call for creating an application, providing the specifics of the application to the managed service for Apache Flink, and then you call a subsequent API call to start the application, pointing to the jar file that you provided. And then managed service for Apache Flink takes care of provisioning, planning, and providing the infrastructure, determining number of task slots per the defined parallelism for you, and then we'll run that job for you on AWS. And you get the integration with the services such as Amazon MSK, Amazon Kinesis data streams, and also you can provide the open source sources and sync connectors to ingest the data and processing delivery to various destinations in AWS. One more thing you get through the service is the configuration management. So you basically get all very nice versioning and version control over the configurations. I will talk more about the configuration in a bit. So let's see how scaling looks like in Apache Flink. Didn't we wish that it was as simple as just saying, I need a parallelism of 12 instead of 4? And then the service magically scales? That's exactly what you get from managed service for Apache Flink. So you basically provide the number of parallelism. By default, managed service for Apache Flink match up the parallelism you define to something known as KPU, or Compute Processing Unit, that would basically provide you, Kinesis Processing Unit, that would provide you 1 CPU, 4 gigabytes of memory, and also 50 gigabytes of the block storage for the parallelism that you need. But then some customers have IO-intensive jobs, and they want to basically provision less KPU for the same job and get the same parallelism. For those only workloads, we recommend increasing the parallelism per KPU. Basically, that would be packing more threads into one KPU. And then remember when I said you would need to shut down the job and deploy a new cluster? That could take up to 15 minutes if you're basically just, this happens during a failure, and then you need to restart a cluster as a result of hardware failure. And if it's a new deployment, it could even take up to 25 minutes for you to do all this process manually. But with managed service for Apache Flink, because it has mechanisms behind the scene for warm pooling and other mechanism, the operator experience is mostly around 5 minutes. So you get basically the less downtime, and that means less downtime for your streaming jobs. You get also other capabilities. I talked about the configuration and configuration management. What if you want to upgrade to a new version of the Flink? If you want to do it on your own, it means that you need to build a new cluster with new Flink version, and then you basically build the application with new Flink and deploy it again and test it, making sure it works. If it doesn't work, then you need to roll back. You get that automation automatically out of the box with managed service for Apache Flink with in-place Apache Flink version upgrade. And then you also get automatic rollback. Should you introduce a new configuration that causes the job fail and cannot restart, then you can opt into that option, and then it will automatically roll back to the last good configuration version for you. And also, it does some compatibility check for you. So if you deploy a new version and it's not compatible for some reason with the snapshot of the previous job, then it basically rejects that change. And also, you get to start a new job with the new Flink version with the save point of the previous job with the lower Flink version, which is really nice. So what is the conclusion here? If you're planning to build a platform to operate and run streaming workloads at the highest scale, not only it's not just the scale or the parallelism that matters. It means that you need to be able to manage all those workloads at the highest scale at the same time, cost effectively, and you need a cost-effective environment that lets you to do more. Also, you want to do that at high scale with resiliency. You want all these jobs to automatically recover on their own. You need the increased resiliency, for example, through active-active or active-passive multi-region architecture. So you don't want to just build it for high scale and then you get no resiliency and high availability. And then also you need to really think about enterprise-grade security and connectivity. With all the manual operation, those are going to be error-prone, and there are risks for security and compliance and steps that they're missing out. And then we need to really think it end-to-end, not only about the Kafka, not only about the Flink, and we need to think it from the place and time that the data is ingested and from the point that the data is being delivered. And that's usually not the same AWS account or not the same AWS VPC. So we need to think about the services that will give us the best connectivity and integration across the board. With that, I would leave you with some of the resources to read more. Please learn and be curious. Scan these QRs or take a picture now, and then you can use it later to learn more about the best practices that we talked about here. And then finally, I have a plea. Please, please, please pay attention to our survey. We really use your input to improve these sessions for next sessions, for the future sessions, and we're really looking forward to get connected with you. Thank you very much.